So now let's look at an example. What I want to do is to do each of these four questions. The first question asks you to classify each of the compounds as strong field ligands or weak field ligands. So look at Cl- and Cn-. Based upon your answer to part 1, draw the crystal field splitting diagram representing the splitting of the d orbitals in the two complexes. Make sure that you draw in the electrons associated with the d orbitals on both complexes. Third, how many unpaired electrons does each transition metal cation have? And then finally, calculate the spin-only magnetic moment for each coordination compound. So, the answer to question 1 is that Cl- is a weak field ligand, and you don't need to know the value of the ligand field splitting energy. Just remembering the spectrochemical series, Cl- should be a weak field ligand. So, you should get high spin complexes from this. Cn- is a strong field ligand, splits the orbitals very well, and you should get low spin complexes all the time with Cn-. So now let's draw the crystal field splitting diagrams for the two complexes. Remember, we're looking at just the d orbitals on the metal cation in the complex and their electrons. These are both octahedral compounds. So you should get the characteristic Eg T2G splitting. The number of electrons that chromium has, this is chromium 2+, is 4 electrons. So you have to arrange the 4 electrons in one of two ways. When you have the weak field ligand, Cl-, that splits the d orbitals very poorly. So you should have 1, 2, 3, 4 unpaired electrons for Cr2+ in CrCl6 4-. In CrCn6 4-, you have a strong field ligand, so this difference in energy between the T2G and Eg orbitals should be much greater, giving only a low spin complex. So you should have only 2 unpaired electrons. Now, based upon the number of unpaired electrons that you've determined, you should calculate the spin-only magnetic moment for each coordination compound. For CrCl6 4-, it has 4 unpaired electrons, so we take the square root of all of 4 times 4 plus 2, 6 times 4 is 24. The square root of 24 ends up being about 4.89 Bohr magnetons. So the units on this are Bohr magnetons. Don't forget, you have to include the units. For CrCn6 4-, you only have 2 unpaired electrons. So 2 times 4 is 8. The square root of 8 is 2.83. So the magnetic moment, spin-only component, should be 2.83 Bohr magnetons. Now, let's think about what the results from example 4.2 tell us. First, it tells us the type of ligand and the number of unpaired electrons a transition metal cation has in a coordination compound will affect its magnetic moment. The more unpaired electrons a transition metal cation has, the greater the magnetic moment for the compound should be. The spin-only magnetic moment can be used to predict the number of unpaired electrons in a compound as well. And I suggest that you take a look at page 78, table 4.3, to help you out with that. So the second property that we will look at is absorption spectroscopy. Dr. Bennett has gone over this extensively in organic chemistry, where you take a sample of a compound, you hit it with light of specific wavelengths, and you see which light it absorbs. So I'll let you review the theory on your own. You will not be tested over the theory in this class. It's important to know that coordination compounds are very colorful, though, and that the colors of the compounds come from absorption of a part of the visible spectrum. The colors that aren't absorbed by the compound are transmitted by the substance. So the colors that we see in these different compounds are transmitted light. Now, there's a very simple method that you can use to determine what color of light is absorbed primarily by a compound. So, for example, if a compound has a blue color, what color light does it absorb? Well, just draw a color wheel. Remember Roy G. Biv. And then if you say it absorbs blue light, the color opposite from it, orange, is the light that it will absorb. Now, the next question that you might come up with is, why do different compounds containing identical transition metal cations have different colors? Well, remember, it's not only depending upon the transition metal cation, it also depends upon the ligands, because the ligands will split the d orbitals differently. If you have a strong field ligands that split the d orbitals very, very much, you can have a low spin complex. That changes the electronic structure of the compound. If you have a weak field ligand, though, you'll have a high spin complex, and that should lead to different physical properties. Also, changes in coordination number or molecular geometries will affect the absorption spectra of a compound. There are methods to determining the crystal field splitting energies based upon absorption spectra. In its simplest form, absorption spectra basically measures electronic excitations, electrons being excited from one orbital to another. The frequency of light that's associated with exciting electrons can be used to determine the crystal field splitting energies using the following method. Delta, remember, that's the crystal field splitting energy, is equal to Planck's constant times the speed of light times Avogadro's number divided by the wavelength that the light has. Now, make sure that you note that the wavelength, which may be given to you in nanometers, should be in meters in this case. An alternative form you might see of this is Planck's constant times the speed of light times the wave number in reciprocal meters times Avogadro's number. You'll get an opportunity to try some of this on your next homework set with determining the crystal field splitting energies of compounds. This will be where our exam 1 material ends. The reactions of coordination compounds, which will end our section on coordination chemistry, will be tested on the final and on the second quiz. Expect a study guide to be posted this weekend for exam 1 and a practice exam as well.